Today we're going to begin talking about chemical equilibrium. Chemical equilibrium is the point at which both the forward and reverse reactions in a chemical equation have equal reaction rates. When this happens, the amounts of each substance in the chemical equation will not change, despite the fact that both reactants still proceed. So the reaction hasn't stopped, but at least in some chemical reactions, what happens is if you start out with reactants, as the reactants get used up, eventually what is going to happen is some of the products are going to reverse and make reactants again. So eventually you'll get to a point where the forward reaction and the reverse reaction and the forward reaction will happen at the same rate, and that is the equilibrium state. Not every reaction will result in an equilibrium state. For example, if you burn paper, you can't do a reverse reaction for burning paper. The products that you have, carbon dioxide and water, will not reverse and reform paper. The same is true for many reactions. You can't undo them. But for a lot of reactions, you can. A reverse reaction will happen, especially reactions that are in solutions. And this graph is just a basic generic graph. It's not, different reactions are going to look slightly different. So for example, you may end up with a much faster forward reaction, and you may reach the equilibrium state much faster. Or you may end up with a much slower forward reaction, and it might take a really long time before you reach the equilibrium state. Again, that's going to vary from reaction to reaction. But this is just a general way that equilibrium state can be viewed. So we are going to talk about the equilibrium constant. So if a reaction occurs and equilibrium eventually gets reached, we can calculate what's called an equilibrium constant, and that's represented by a capital K. So look at this general reaction here. This is just a generic, again, coefficients and reactants and products. We can substitute any coefficients for A or the reactants for any of these with a real chemical reaction. But what happens is, so K can be calculated. The concentration, now this is different than the kinetics chapter. When we talked about the rate equations, we did not deal with the products at all. We were only dealing with reactants. In the equilibrium equation, we are dealing with these. We're going to look at the ratio between the products divided by reactants. So what this equation means is the concentration of the two products at equilibrium divided by the concentration of the reactants at equilibrium, that's what the EQ stands for, is going to give us an equilibrium constant. Now these exponents, C for C, D for D, A for A, and B for B, represent these coefficients. So you don't have to figure out what the exponents are. They're just given to you from the calculation. All right, so moving down to the bottom of your worksheet, I'm going to help go through the fill in the blanks steps here. Equilibrium does not mean that the concentrations of the products and reactants are the same, but that the ratio of concentrations of products to the concentrations of reactants remains constant. Therefore, an equilibrium constant can be calculated. It will remain constant throughout the reaction. The value of the equilibrium constant for a given reaction changes with temperature. As you might expect, temperature always affects reaction rates. When the K is large, the equilibrium is weighted toward the products. So if this is a large K, that means the numerator of this expression is going to be larger than the denominator. That means the concentration of the products is going to be greater than the concentration of the reactants. When K is small, think of it's less than 0, that means these concentrations are going to be greater than the products. So when K is small, the equilibrium is weighted toward the reactant side. and few products will be formed. That means the reaction may not occur very long at all before equilibrium is achieved. A couple other things to note. When a solid appears in a chemical equation, it is not included in the equilibrium constant, in the equilibrium constant. And when a liquid appears in a chemical equation, it is also not included in the equilibrium constant equation. So this does not apply to things in the aqueous phase. It is included. Okay, we're going to go through some of these. First thing we're going to do is we're just going to practice writing the expressions. Okay, so write the equilibrium expressions for each of the following reactants. Okay, so this first one, this is ammonium nitrate, and it forms nitrous oxide and water. So the phases are all included. This is a solid, this is a gas, this is a gas. If it's solid, we don't include it in the equilibrium constant. So here's how we would write the expression. We take the concentration of anything that's not a solid or a liquid, and we're going to do the products over the reactants. Since there's no reactants, this is only going to be products. So the concentration, dinitrogen oxide, monoxide, its coefficient is 1, so its exponent is going to be 1, times the concentration of water, and its coefficient is 2, so its exponent is 2. That is how you would write the equilibrium expression. Now let's look at the units here. So we do concentration is in molarity. So if I have a molarity here with an exponent of 1 and a molarity here, exponent of 2 times M2, I'm not meaning this to look like it's on the denominator. So the unit that we would use would be M cubed. So we don't need that, put that in the equilibrium expression. I just showed you how we would do that. Okay, let's look at the next one. Okay, we have a gas, we have a liquid, and we have a liquid in the products. We don't include liquids in the equilibrium expression, so we're not going to use that. Equilibrium expression, we're going to do the products over the reactants. Since that's the only product and it's not included, our numerator is just going to be 1 divided by the concentration of the only reactant, and its coefficient happens to be 1. So that is a simpler equilibrium expression. Its unit would be 1 over M. Okay, look at the third one. Here again, we have a solid, not included, a solid, not included, and a gas. Equilibrium expression, the concentration of the products here, this is the only product, oxygen, concentration of oxygen, coefficient is 3, exponent is 3. Nothing is going to go on the denominator. That is the expression for that one. Its unit is going to be M cubed. Concentration of oxygen would be expressed in molarity. Molarity to the third power would be molarity cubed. Okay, now let's do some problems with numbers involved here. Okay, so the equilibrium constant for a particular reaction is given by the following. What is the balanced chemical equation for this equilibrium? So this one isn't going to involve math just yet. Here we're going to do the reverse of what we just did. We want to write the chemical reaction based upon this expression. Remember, the products are in the numerator. Reactants are on the denominator. So these are the reactants. So we want to look at the exponents. Those are going to be the coefficients. So we have CS2 plus 4H2. Products are going to be the numerator. And that exponent is 2 plus CH4. You don't need to balance it because those exponents are doing the balancing for you. If you would check, you would see that this is balanced. The only thing this doesn't tell us is the phases. The phases, they would either be gases or aqueous phase. So, it doesn't tell us. We know they're not solids or liquids because they wouldn't even show up in the equilibrium expression at all. Okay, number 5. What is the equilibrium constant for the following reaction? It tells us the concentrations. So we want to calculate K from that. So the first thing we're going to do is let's write the equilibrium constant. Okay? So we're going to look at the equation, the products, because they're all gases, so that means they're all going to be included. So this is the only product. It's going to go in the numerator. Exponent 2, because the coefficient is 2, divided by the products, concentration of N2 times the concentration of O2, and that exponent is going to be 3 because that's 3. Okay, then we're going to put the numbers in, the numbers given to us in the problem. Ammonia concentration 1.14 molar squared divided by nitrogen's concentration times hydrogen's concentration, and that's going to be cubed. Okay, so do the math on your calculator, multiply these. If you used your parentheses key, you can do 1.14, square that, divided by, and then parentheses, and multiply this together. You just got to be really careful on your calculator. Another option is just to square this, write it down. Cube that, multiply that, write that down, and then do your division. You will get 838 for your numerical value of that constant. And look at the units. Here I've got m squared in the numerator divided by m times m to the 4th in the denominator, using your rules of exponents. M squared divided by m, this should be third, divided by m to the 4th is going to be m to the 2nd in the denominator. So that is my equilibrium constant. Okay, the questions asked, is the reaction weighted toward the reactants or the products? Since this number, if it's around, if you end up with an equilibrium expression around 1, it's going to be equally balanced between reactants and products. If it's much larger than 1, this is quite a bit larger than 1, it's going to be weighted toward the products because the numerator number is going to be larger than the denominator, so it's related toward the products. Okay, number 6. A chemist is studying the following reaction. And it tells the concentration he starts with, and the reaction reaches equilibrium when those concentrations of products are achieved, or reactants. At that point, the concentrations. I'm not going to read through each concentration, but what is the equilibrium constant for this reaction? So this is just like we did. So this is what he starts with. We want to know what the concentrations are when he ends. So let's write the expression first. They're all gases, so we're going to include them all in our expression. First of all, the products. Divided by the reactants. Remember, all these coefficients are what my exponents are. Okay, now we're going to put these values in. My concentration at that point, that's the point where we're wanting to use these concentrations. NO2 is 0.40, and that's to the 4th power. H2O, 0.60, and that's to the 6th power. NH3, 0.8. When NH3 is this is what the NH3 start out with, but at equilibrium, it's this value. And that's to the 4th power. And O2 is 2.7 when it's at equilibrium. This problem had more information than you needed, so you had to figure out what numbers you were actually looking for. Okay. Multiply it out. Pause the video, see if you get the right answer. Going to end up with an equilibrium constant 2.6 times 10 to the minus 6. Okay, and I'm going to look at my units. We have molarity to the 4th times molarity to the 6th divided by molarity to the 4th times molarity to the 7th. So using your rules of algebra and exponents, it's going to be 1 over m. So this is my equilibrium constant. Is this reaction weighted toward the reactants or the products? Since this is a very small number, that means there wasn't very much product made in relationship to the reactants. It's weighted toward the reactants. All right, one more problem here. So this one is a little different. Here it says the following reaction has an equilibrium constant of 17 molarity squared. We already know the equilibrium constant. The chemist measures the concentrations of each of these, and we want to know, is it at equilibrium? So what I'm going to do is I'm going to write my expression. They're all gases, so they're all included. And I'm going to calculate what I get when I use these values. Okay, and then I'm going to see if I get a number of 17, that means yes, it is at equilibrium. If it's not, then no, it's not at equilibrium. Okay. In concentration of N2, just plugging these in from the numbers given above. Do the math. You should end up with 21. The unit would be molarity squared. So that's what I calculate at these concentrations. When it's at equilibrium, it should be 17. So it is not at equilibrium. So which way does it need to shift? This number needs to get smaller. The only way this is going to get smaller is if this ratio of products to reactants, this gets smaller. So that means it needs to shift to the left, needs to shift toward reactants for equilibrium to be achieved. Okay, that's the end of this session. The next one we'll be talking about how shifts occur, like how can we make shifts occur. Okay, that's it for this one.